we've seen that what goes in must come out unless something else happens to it. One of the things that can happen is chemical reaction, but another thing is accumulation. So in this case, accumulation is equal to the difference between what goes in and what goes out. Now, to put this in algebraic terms, the accumulation is the change in number of moles in the system with time. So dN, that's the number of moles of our species, in the case of problem number 4, the CO2, dt. And notice that this has units, moles per minute. So every term in the balance equation has to have the same units. What goes in is the molar flow rate. We'll call that N in, and that's that 50 grams per minute of carbon dioxide, changed to moles, of course. So that's moles per minute of carbon dioxide. Now, what leaves can be expressed as the volumetric flow rate times the concentration. So we have the volumetric flow rate, cubic feet per minute, times the concentration, which is moles per cubic foot. The cubic feet cancel and we have moles per minute, as we should. Now the concentration changes with time just like the number of moles, and so it'd be handy to change concentration into the same unit as moles. So concentration then is the number of moles divided by the volume of the system, which is the volume, area times height of the room. So we have moles per cubic foot, that's the concentration. So substituting that in to the equation, we have N in minus V, the volumetric flow rate, divided by the volume of the system, times the number of moles in the system. So there's an equation that we can use to solve for the number of moles in the system as a function of time. So here's our equation again. The change in number of moles with time is equal to the number of moles coming in per time minus the number of moles leaving due to that ventilation of the room. And every differential equation has to have an initial or boundary condition. In this case, it's an initial condition. That n is equal to 0. We assume that at time equals 0. Now we can use the Euler equation. You could, of course, solve this algebraically, but we'll use the Euler solution just as something convenient. Rewriting this with dn dt being delta n delta t, we have n at some time is equal to n, which I'll call prime at a time period before this, plus the change in time, that's our time increment, times the right-hand side of the equation, which is n in, should put a little dot above that, minus v over the volume, volumetric flow rate over volume, times that n at the previous condition, like that. And then we set up a spreadsheet where we have the columns T, N, and then you can also have a calculation of Y, the mole fraction. So time will start off at 0, and we set n equals 0 at that time, and the mole fraction will be 0. So you can set those. Now, whatever increments you want to use, let's say 10 minutes. We'll calculate a new n based on the previous n, which was 0 in this case, using the Euler equation, and calculate a new y. We could do that all the way to 480 minutes, which is 8 hours, and we'll get a number of moles, and we'll calculate a mole fraction. And the question is this mole fraction greater than some amount that is harmful, that would cause the Hamburglar to be unconscious or some other ill effect? So I read someplace it's 10%. Check that out. So the question would be then, is y greater than 0.1 at 8 hours? And there we go.